So, so this is about the fuel gas cleanup. When we, for those, this is not their area. There is difference between flue gas and fuel gas, as you know. Flue gas is what is generated from combustor. Fuel gas, what is generated from gasifier because of the reducing environment. So, but anything that you want to do with the gas, whether that is for power generation in gas turbine or for chemicals production, you need to clean the gas up because the gas turbine manufacturers are very, very strict as far as what they can tolerate. So that's why is the need for considering fuel gas cleanup. So what is fuel gas cleanup? It means several things. So one is, of course, the gas cleanup means getting rid of the pollutants, and the pollutants can be a whole lot of things. The particulates and the gaseous pollutants, and within the gaseous pollutants there may be so many different things as well. The sulfur compounds, and as I said the other day, that for sulfur, the main form in which it comes out is not sulfur dioxide at all. It's in the form of hydrogen sulfide, carbonyl sulfide, COS, and also CS2 carbon disulfide. Predominantly hydrogen sulfide because majority of the sulfur is present in the coal, in most coals are present as organic sulfur. That's the reason. And progressively in the other ones, CS2 being the smallest. COS, if it comes out, then often COS can be hydrolyzed with steam to form H2S and CO2. So you get that H2S back, and then if you get H2S back, then with the help of Claus process, CLAUS, Claus process, you can generate elemental sulfur. So some of the large plants, particularly the Polk plant, I think, Polk Power's Tampa plant has sulfur recovery unit, which they sell to the market. Nitrogen is the other gaseous pollutant. It comes out as nitrogen, ammonia and hydrogen cyanide, as I mentioned before. Halides, predominantly hydrogen chloride, but in extreme cases, not extreme cases, in very rare cases, with high fluorine coals, that can also come out as hydrogen fluoride, but there are not very many. But I've listed there just because it is possible. Then you have the alkalis. Alkali vapors that definitely come out as long as the gas temperature is above 600 Celsius. All the sodium and the potassium species. This could be hydroxides of sodium, of course sodium chloride as well. And a few other species in smaller fractions. Then you can also have the heavy metals, depending on how much they are present in the first case. So the heavy metals can be vanadium, can be lead, can be selenium, can be few other species as well. But vanadium is of strong interest. Calcium is another one, and mercury is another one that I have listed, which those have to be cleaned up. Calcium has to be cleaned up because if these are not cleaned up, the gaseous calcium species, the hydroxide is one example, chloride can be another one, then they can go and deposit into the gas turbine blades. So that's why. and mercury, as we know. Mercury is a classic case. It is it can come out as elemental mercury or oxidized mercury, depending on whether it is a gasifier or a combustor. Oxidized mercury is lesser of an issue that can be captured in the ESP or the back filter, oxidized mercury. And but the elemental mercury is what comes out from gasifiers. That is difficult to capture by normal means. So Eastman Kodak developed an activated carbon bed based mercury capture process back in the 80s, and that was demonstrated successfully, and that is predominantly now the used method for mercury through adsorption onto the activated carbon bed. How you then dispose the mercury saturated activated carbon bed, that's a different issue. But at least it's gone from the gas phase. Okay. So at the bottom, second large bullet point, I've listed why we need to clean the gas. Obviously, to meet the requirements of the gas turbine or the fuel cells requirement, whatever be the use, or for the chemical synthesis requirement. And on top of that, of course, there are the environmental regulations. For all of this, you have very strict regulation guidelines by the EPAs in almost all the countries, which have to be met. And but gas cleaning has a significant implications on the cost. In order to clean up the gas, meet the requirements of the equipment or meet the requirements for the statutory bodies, the efficiency will drop, therefore the cost will increase, and the efficiency will drop depending on whether you are looking at hot gas cleanup or cold gas cleanup or somewhere in between. So cold gas cleanup definition is easy. You're cooling everything down so as to take all the alkalis out, all the condensable species out, particularly the alkali and the moistures are all gone. Hot gas cleaning obviously avoids the exergetic losses, but then it's easier said than done, because even now the hot gas cleanup is not fully developed, and especially at 800, 900 degrees centigrade is still a major challenge. There is a lot of DOE funded work, US Department of Energy funded work on hot gas cleanup that went on in the mid-90s when our PFBC was still in vogue. Even though the environmental regulations were less stringent than now, and also gasification where interest were peaking. So in order to achieve higher efficiency, there was a strong impetus on developing hot gas cleanup system. But despite considerable amount of effort and money spent, predominantly government money, hot gas cleanup has still not seen the light of commercialization. So a compromise has been made, which is warm gas cleanup, and which is somewhere in between. It's not as cold as cold gas cleanup, 400 degrees or so. Mercury is through adsorption. So, of course, the adsorption strength is less at high temperature, but it can bond better and better as you reduce the temperature. So at 1 gas cleanup, it will still be okay. Or all below 600 will be fine. Alkali and halide. So we have the particulates, the gaseous pollutants. So let's focus on the particulates. What are used is for particulate removal. Usually these are done in 2 stages because, as I mentioned, you generate a size, distributed size as far as the particulates are concerned in the flying particulates. So the first cut is to separate them through cyclones, but these are for quartz particles only. Now the question is, what is quartz particle? What's the cutoff of the quartz particle? Or 10 micron? Anything below that, cyclones will not be that effective. They will pass through. So you then have to have other means separately, but at least what will go past the cyclone will not be as widely distributed a distribution as before. It will be narrower and finer, which means those then lend themselves to separation by the candle filters. Candle filters, why the name candle? Because they are like candles, look like candles, but not small candles. They are 2 meter, 3 meter, 4 meter candles. They can be made of metallic filter, or they can be made of ceramic barrier filter. So I'll come to each one of those one by one. At the metallic filters, they are easily, both cyclones and the metallic filters will tolerate high temperature. Metallic cyclone, of course, if it is refractory lined, temperature is not an issue. And usually it is refractory lined. Unless the manufacturer says that no, nothing in my technology is refractory lining. So it will be just normal metallic cyclone with insulation. Either way, high temperature is not a problem. But for the metallic filters, the temperatures depend on what the metal is. Because as you would expect, the gas is composed of not just carbon monoxide, hydrogen, carbon dioxide, methane, etc. But it also consists of hydrogen sulfide, so the sulfide gases, chlorides, unless you have cooled it down before the metallic filter, and the sticky hydroxides, etc. So the chlorides and the sulfides at those temperatures, and also because of the pressure, they will give rise to stress corrosion, the metal filters. Usually, so there was a considerable development or considerable impetus for the development of the metals, for appropriate metals for metallic filters, and these were done predominantly by the private company. So Paul, P-A-L-L, Paul, was a front runner at one point of time. Now there are others as well who developed iron aluminide as being one of the relatively inexpensive, not very expensive, but very long lasting. But most importantly, they are resistant to corrosion and corrosion from sulfur and alkali attack. So iron aluminide long candles you could easily see 4 or 5 meters tall candles circulating from the top. And we'll see in the next slide how these are hung, how these are operated, and those sort of things. Because they also, if they are not properly maintained, they can have their fair share of problems. Then, apart from the metallic filters, the mostly used are the ceramic barrier filters. As the name suggests, ceramics do not have a lot less temperature limitation. Ceramics can go to very, very high temperature, even 13, 14, 1500, not a problem. As long as they are not cycling too much, as long as there are not a significant pressure swing that occurs across them. So they have very strong temperature resistance. They can be made relatively easily. They are across them, the they result in relatively low pressure and low temperature drop. So that's the positive. And what are those ceramics? They are silicon carbide or silicon nitride or alumina or alumina malite. Malite is silicon. So aluminosilicate essentially. So all sorts of materials for ceramic candles have been available. But they have a problem. What is the problem? That they don't like pressure shocks. If that be the case, they crack. And so pressure itself is not a problem, but if the pressure swings, so if you're running at say 30 bar, that itself will not be a problem. But if all of a sudden the pressure drops for the gasifier, all of a sudden, for example, say 10 bar, and then that's transmitted all the way across, then you have a pressure drop, and that's something that it will, and then when you bring the pressure back up again, if you want to do it quickly, they will not like it. The other one is the most important one. In fluid mechanics, you have learned about flow-induced vibration, right? Flow-induced vibration and associated shock is something that the candle filters absolutely detest. They crack like anything, just like toys. And remember that these are very tall, supported from the top, hanging downwards items. So any flow-induced vibration, they can swing by quite a number of centimeters. And so from the supports, they can snap. So their shock resistance was really shocking. So that's a mechanical design thing, so that the flow-induced vibration is reduced, but flow-induced vibration can never be eliminated completely. As soon as there are flow swings, there will be flow-induced vibration. The other thing is ash bridging. So if you have two candles coming down side by side, then if there is ash buildup, then obviously they can bridge. The ash can form a bridge, and the ceramic candles filters are very much they do result in, I wouldn't call promote, but they result in more ash bridging than the metallic ones. The ash finds it easier to grow on the ceramic candles surface than on the polished surfaces of the metals, and stick and grow and stick and grow and stick and grow. So that's the problem. And then the long-term operation under high temperature, reducing atmosphere, is yet to be demonstrated. I say that despite some of the claims to the contrary that I have seen. My definition of the long term is 8,000 hours. And so 5,000, 6,000 intermittent cumulative is one thing, but continuous, that is another thing. So both of them have their pluses and minuses. Ceramic candle filters are cheaper, obviously, and the metallic filters, particularly the iron aluminite, are dearer. So it's the high capex versus low capex, low opex, or low capex versus high opex issue, and relatively easy availability. Those are the issues that the plant suppliers have to grapple with before selecting one way or the other. There are not very many suppliers of metallic filters, but there are lots of suppliers of ceramic candle filters. Now, so every cycle, so Cyclone Design is now pretty standard, and you can actually get some of the Cyclone Design softwares even available in Google. What it is that depending on the gas velocity and the particle size, how much particles will be separated and which particles will be separated, that's decided. Okay. Now, in a gasifier, the gas flow rate is constant. If you are generating 400 megawatt watt electricity worth of gases, then you know what will be the gas flow rate for your coal. So that's not going to change widely from day 1 or day 365. So flow rate is changing. But if the particles sizes, they change for whatever reason, then the cyclone won't be able to tolerate if there are all of a sudden significantly small particle sizes coming. The other thing is, if you want to design a cyclone to separate out right from sub-micron to 30, 40 micron, you can do that. Theoretically, you can do that. But whether effectively it will do it is another question. So, in Cyclone Design, what we have is something called effective the cutoff size, above which it will very efficiently cut off everything, separate out everything, it is done, and then allow the others to go together entrained with the gas. So rather than trying to design a super duper expensive, unpredictable cyclone, a large one, it's much better to do one that will operate efficiently, performance well predictable over a longer term, cut it off all the above a certain size, and rest smaller ones, get it done through the other means. So that's the conservative but sure way of separating out the particles. So you cannot, to answer your question, you cannot replace the metallic filters completely by multiple cyclones. It will be difficult. So here is an example of how the filter candles are arranged. So to some of you this may be known. So it's a cylindrical vessel with a throat at the bottom, a conical section at the bottom. The gases come from the left side, and then they go through the surface of the candles, which are essentially hollow tubes, but with very, very fine pores. So the solids then on impingement find the resistance to go through it. So the coarser ones through the impingement will fall down. Some of them will stick to the surface, and some of them will go inside the tube and then will come out through in here, and that's where the remaining particles, fine particles, together with the gases will come out. So so it's not quite solids free, but majority of solids free, cleaner gas comes out from here. So that's how this is the these are the filter candles. So they can be metallic, they can be ceramics, and but depending on whether they are metals or they are ceramics, there are different ways of hanging them, supporting them from the top, because as you can imagine, this can this can swing, being anchored at the top. So that's how they are designed. So they will all be hanging. Now, what is not shown in here is that there is shown. There is something called the Purge Gas Inlet. So what does the Purge Gas Inlet do? So you are purging the gas into the hollow tubes, so that it then tries to go from inside out and then dislodges the particles which have been sticking onto the external surface of the tube. And this is a it has a very important function. How it is done? The frequency of purging and the amount of purging is a very critically controlled parameter in a gasification plant. So it seems innocuous, but it's an extremely experience-driven number or numbers, these two. Because if you are putting in too much of a purge gas, then what will happen is it will disturb the hydrodynamics inside the cyclone. It can give the pressure drop in the opposite direction, and a whole lot of problems can happen. If you do it too low and too infrequently, then there will be ash bridging. And then also it also affects the quality of the syngas for that period. So if you are purging it for 2-3 minutes, then for that 2-3 minutes, syngas quality is decreasing, right? Because it's all high pressure nitrogen. So it has to be kept very low. So that's the important bit. Tar is really driving you crazy. Yes, that's right. So if there is tar, then you will have to keep provision to crack it away. So of course you will not send oxygen to it, because then it can catch fire. So the only option is the inert gas, just like inert nitrogen purge gas. Inert steam will crack it, and then you will have less of a problem. But it can be a problem, particularly if you are running biomass and biomass at low temperatures, then obviously it can be a problem. So is it making sense, Madhusri? Madhusri, yes, it is making sense. Good. So, so I got your name almost right in the first instance, and second instance otherwise I'll get it right. So, there is a limit that's important to remember. This purely comes from gas turbine and fuel cell specification. If the particles, with the particulates, then we are looking at no more than 2 parts per million weight. Sulfur, 20 parts per million volume. Halides, 1 parts per million weight, and this is what is crazy. and then the heavy metals, and the nitrogen compounds. That varies from country to country. The gas turbine manufacturers will take care of the nitrogen simply by diluting the gas, whatever going into it, by staged nitrogen introduction at the gas turbine inlet, so it's not a problem. And calcium is from the deposition point of view. But these are the figures. I suspect the emission limit for the particulates in some countries have become more stringent, in the sense that they now have separate limits for PM 2.5 and PM 10. Say 20 years ago, it was difficult to detect quantitatively or analyze and measure quantitatively PM 2.5, but now you have that means. So now the EPA can enforce it even more, and it is still it is a major issue in many countries. So you missed all the interesting bits, Shantanu. So some fantastic presentations from everyone on so many diverse topics, you know. Yes, but you know, the live one is the more important thing than the recording. The live one is always the most important one. Okay. Anyway, so if this is any indication, I think the next one will be equally important, interesting. So now let's move away from particulates to the sulfur cases. So as I said, it depends on the sulfur forms in the coal. COS is mainly removed by hydrolysis, as it is shown, and the lower temperature drives it to the forward direction. But again, that depends on the type of gasification. If you are involved in fluidized bed gasification, then fluidized beds provide the right temperature for in-bed sulfur capture, so that you can capture majority of the sulfur in the bed, because fluidized beds operate around the ideal limestone-based, calcium-based sulfur dioxide, sulfur capture at around 850 or so. So in bed you can do it, and then whatever remains, which is a much smaller fraction, which then can be done in a separate desulfurization bed if required, together with the fuel. So even though they come from different hoppers, but eventually they get mixed closer to the entry point of the gasifier, and then essentially they get mishmashed and then captured. So the important thing is to ensure that they go to the bed together, so that in-bed capture is available. That in-bed capture is not available, is not possible in entrained flow gasification. So entrained flow gasification, you have to do everything outside, separate outside. So that's the mechanism for the capture of it. CO and H2S developing CAS and H2O. But if you are supplying the calcium oxide as calcium carbonate, which is normally the case, of course the calcium carbonate will decarbonize fast and give you carbon dioxide and calcium oxide, and then the same thing will happen. It is just that you will get extra CO2. And but then what happens with the COS and the H2S is that it's not possible to do it with, but they are smaller proportion anyway, so they can go into the hydrolysis if required. If they are in a very large proportion, then they go to a hydrolyzing chamber around 250 degrees or so with steam, and can give you the first one, the first reaction to convert it to H2S. and then the Klaus process and so on. Then people have also tried other options, the regenerable metal oxide solvents. One of the problems why going away from calcium oxide based to metal solvents, calcium oxide is cheap. But the problem with calcium oxide is that it's not 100% efficient. So if you are getting about 60% efficiency of capture, you're doing well. If you're getting 70 to 80, you are doing exceptionally well. The other 20% just goes out. So it's a huge loss. Why it is mainly because the capture of the sulfur species, gaseous sulfur species on solid calcium oxide is a kinetic gas-solid reaction, kinetically driven gas-solid reaction. So the residence time is important, but as you would expect in the gas phase of whether a fluidized bed or intent for gasifier, in the gas phase there's not much time, right? So that's one thing. And second thing is you'll find a lot of literature which is suggesting, and Ben Anthony was, as we were discussing, Ben Anthony was the master of it. The calcium oxide gets coated with other things, and then it cannot react with the incoming hydrogen sulfide anymore. So that's the problem. And if that happens, you cannot regenerate the calcium oxide. Very, very difficult. Then you will be looking at spending more energy to do it, which is not worth. So that prompted the industries to look for anything other than calcium oxide, even though calcium oxide is cheaper, decidedly cheaper. So that's where this metal oxide based ones came into consideration. And what are those metal oxides? We'll come to that. But let's just say that is the metal oxide plus sulfur dioxide will give you the metal sulfide and then the water vapor. And the beauty of the metal sulfides is that you can actually regenerate it with air by the chemical looping principle. So you can keep that in mind. And that's the mechanism. Okay. Regeneration is about 800 or 900. The beauty of it is that it's an exothermic reaction. So you are not supplying additional heat. The problem is how you can use that exothermic heat. But using exothermic heat is not a problem. This exactly falls in the chemical looping principle where I'm digressing a little bit, where the fuel reactor, which is a gasifier, is endothermic, and the oxygen carrier gets reduced to lower valence form, and then is regenerated back to the oxygenized form or oxidized form through an exothermic reaction. Anything that you are using with oxygen for combustion purposes is essentially oxidizing. So this is regeneration, is nothing but looping, is exothermic. You have excess heat available, you can use that heat somehow within that system. Okay, so that's the metal oxides principle. And so during the regeneration process, you then get sulfur dioxide. And then if it is sulfur dioxide, then you can get elemental sulfur from it by off-the-shelf technologies. So what are these metal oxides? So different companies, considerable amount of R&D were done, and very successful R&D actually. These are the front runners that eventually were settled on. Tin, copper, manganese, iron, zinc based one, copper, then of course cerium as well. we've listed it in increasing order of temperature. There are two sets of temperatures that I have given there. One is the temperature range at which it can capture. The other one is the temperature range within which you can easily regenerate. But it will give rise to higher temperature, but then you can then extract that heat somehow or the other, so that will not be a problem. The efficiencies range from varies within a large range, and that's given in the 1, 2, 3, 4th column, and the last column it tells us that it can bring where it can bring the concentration down to. So some of them can actually bring it down to very low level. There's the ppm. I should have had the units over there, which I did not when I copied and pasted. So they can have different degrees of efficiency, but the good thing is that there are certain metal oxides which can give you very reasonable efficiency and very low final level at the end. So you can easily go for, say, the zinc one. Zinc oxide is not all that expensive anymore. Iron oxide, you can try them. I have seen higher figures than this 25 to 45% that I have that is there in this table from the IEA report. But there are other. The current levels are much higher. Cerium oxide is actually quite expensive, particularly, and cerium oxide. The problem is, one other problem, these are desulfurizing bed, and these are mildly fluidized, mostly fixed bed. If you have fine particles of bed, and if you can keep them fluidized, keeping the fine particles fluidized is not that easy. But if you can keep them fluidized and get the surfaces easily available, then of course you can improve the capture. So a lot of the capturing efficiency improvement is based on the design of it, design of the bed, choice of the size of the particles, gas velocity, etc. Because if it is too much of a pressure drop, then you have got other downstream problems. The gas pressure and the gas temperature will be dropping, and then you will have to overcome a few other issues. So pressure drop is one of the criteria. So to answer your question, I think eventually you will have to decide between the size of the particle, cost of the particles, etc., and their easy availability for replacement. But either way, both zinc and iron oxides, they lend themselves quite well to regeneration. So the inlet, the temperature at which the gases, inlet gases can be tolerated. And the third column is temperature at which this can be regenerated. But the regeneration temperature really doesn't matter much because it's an exothermic reaction. So it's not something that you need to supply it. It will generate exothermic heat which you should be able to utilize. In ppm. Everything is in last one in ppm. Yeah. 40 or so, they will not be effective. They will not be effective because the reactions, the gas-solid reactions will not occur much beyond that temperature at all. So hot glass cleanup, I mean very high temperature, that's what I was discussing, 900 degrees or so, that has been abandoned more or less. Abandoned because it's such a low efficiency thing. There's an enormous research that went on. So now almost everyone has settled on warm gas cleanup. And this is warm gas cleanup. The beauty of it is that it takes care of the alkali and the halides. Below 600, certainly below 550, alkalis are gone. Because the alkali's limit, permissible limit, is very, very low, extremely low. So at the end of the day, the desulfurization is not going to be the deciding factor. As the alkalis, which is going to be the deciding factor, even though it is important, but it's not the. Temperature is the guiding thing. Yeah. This will condense out. So just like water vapor can condense out below a certain temperature depending on its partial pressure. Below 600 degrees is generally accepted norm. But to be on the safe side, you will go even below 550, closer to 500. At those temperatures, the desulfurization also starts to become more and more effective with the readily available metal oxides. Right? So solvent effectiveness is usually determined through laboratory and bench scale studies, and there has been an enormous amount of studies that have been reported in the past. From my younger days I have seen. So a lot of information is available publicly. The mechanical stability of the mechanical and chemical stability of the solvent also determines its effectiveness, as you would expect. If it is mechanically, if it attrites, if it breaks down into smaller ones, then obviously its effectiveness to capture will be changed. Its particle size, the partial pressure of the gases, the other gases that are passing through, carbon dioxide, HCl, and ammonia, that's also important because they can interfere with these metal solvents through reaction. Ammonia, for example, can react with zinc. So these are some of the issues, broader issues that one needs to be mindful. Then, so particles gone, sulfur gone, denitrification. Usually anywhere between 20 to 80% of the fuel nitrogen is liberated as ammonia. So we are not the ammonia. We are not talking about the nitrogen that comes with the air. There will always be some nitrogen, even if you do high purity oxygen. So we are talking about the fuel nitrogen when we talk about ammonia and the hydrogen cyanide that is produced from gasification. So about that, depending on how nitrogen is bonded to the coal, depending on that, mostly it goes to ammonia, the rest goes to hydrogen cyanide, and very little goes as molecular nitrogen. If all of them went as molecular nitrogen, that would have been good, but that's not the case. Varies from coal to coal, and it's mostly 70–80% of it is bonded to the coal matrix, and that's the one which also gets chance to see in its near vicinity the hydrogen, giving the opportunity to generate ammonia and hydrogen cyanide. Combustor, you don't get ammonia because you have oxygen, so ammonia is oxidized to NOx, and that's another set of problem. Right? Whatever is in the coal, which means whatever is in the coal. But its effect is not to be underestimated, because in any gasification work, even in your pyrolysis work, you just try to detect ammonia, you'll find lots of it. So if you can actually, and biomass has a lot of nitrogen in it, so you can even consider selling ammonia if you want to. I'm seriously. So the reported levels, depending on the gasifier types, 1,000 to 5,000 ppm by volume of ammonia, so it's quite huge. Of course, there will be lower emission of ammonia at higher temperature because they crack. Ammonia can be thermally cracked. So from that point of view, the fluidized bed gasifiers will give you more ammonia. And then the ammonia in the fuel gas produces NOx during combustion in gas turbines. So if you don't clean it up, then it will go to the gas turbine, and the gas turbine will, because of the oxygen, it will convert it to NOx, and then you have another problem. Break the bond, elemental nitrogen. So what are the means for reducing NOx? First of all, minimize the ammonia initially produced in the gasifier, if you can. Depends on the operating conditions, but it's difficult to implement. Simple. Because in gasifier you have got so many other operating conditions to manipulate. Just for ammonia it will not make sense. Reduce the formation of ammonia during combustion of fuel gas. So if the ammonia goes there, and then if you are not taking it out, then during the combustion can you stage the fuel gas, so that instead of sending all the fuel gas in one go at the one stage, you stage them, then you reduce less. I think that's what the gas turbine manufacturers, I think, can do. I'm not sure, maybe. After doing so, if NOx is formed from the combustion, then try to remove the NOx from the post-combustion atmosphere and post-combustion gas. And Dr. Dave will know how that has to be done. Or the other option is to remove ammonia from the fuel gas prior to combustion. Now, ammonia is a condensable gas, so the solution is sure. If you bring it below the saturation temperature, corresponding to its partial pressure, corresponding to its presence in the gas, if you bring it down to that temperature, it will condense it out. So if you do it that way, it will also take out the alkalis, which has a very low emission limit. So instead of giving all the oxygen to the ammonia to the entire fuel gas in one go, you give it in separate stages, so that in none of the stages you can exceed. The more oxygen you give, the higher the temperature it can go. So that's how. So yes, staging is a concept that is used in fluidized bed combustor that Professor Shah was telling yesterday. That's how you control fluidized beds, give a lot less NOx. Correct. And same thing for the gas turbines. And so the means for removing ammonium is obviously waste coming, the condensing out, but that comes out of efficiency penalty. Catalytic decomposition using oxides of these compounds at 550 and 800. Ideally, if you can have something, then the next bullet point, and then I'll come to the sub-bullet point, previous one later, combined ammonia and hydrogen sulfide removal. So if you have a metal oxide, which can do both, and zinc is one example, iron is another example. Iron is classic. Iron can do tar cracking, as we were discussing yesterday. There is the gentleman down. Must be sleeping. And iron can also clean can desulfurize. Iron can also do ammonia cracking. So for biomass, fluidized paired gasifier, iron is the way to go, for sure. But biomass doesn't have much sulfur, so you don't have to worry. Selective oxidation, these are all more and more higher level solutions, difficult to implement at large scale. But fundamental scientific point of view, it's fine. So particles gone, sulfur gone, ammonia gone, nitrogen gone. I mean, then what remaining is the trace element, and then of course the halides. So trace elements. So the mercury, cadmium, lead, vanadium, arsenic, selenium, beryllium. These are all trace elements which are present in coal, very low levels, and this is how they stay, the temperature above which they stay in the gas phase. So Sachin, when you do your calculations, when you do your literature review, look at that aspect. Under oxy-CFB condition, oxy-fluidized bed condition, what actually happens to this. A lot of the results have been published. Have a section on that in your literature review on that. I think it will be good because it will immediately tell you what not to do and what temperature to operate the subsequent cooling after the CFB. So there are some good, and you can actually do those through equilibrium calculations. Particulate filtration using ceramic filter is the most effective means of removal of these species, provided you are doing it at below those temperatures. If you are doing it below those temperatures, then at the same time you are also taking out the halides, the alkalides and ammonia. But one other thing is the chromium emission. Chromium has multiple valences. It's the chromium 6 and chromium 3. Chromium 6 in particular is very toxic, very toxic. This is something that you should also look at, Sachin, as what happens to chromium 6. How many people actually do talk of chromium 6 emission? 15 years ago, no one used to bother them. But then when CCS became the focal point, you have to have deep cleaning of the gas. And by deep cleaning also it meant chromium 6. In fact, chromium 6, if you Google, there is a chemical plant in Australia, which I won't name, in a city where I used to live, not very far from that plant. Their extraction system failed. A lot of chromium 6 went, and people got really, really sick because it's really toxic. And eventually that multinational company had to completely shut down and stop production in that site. It's a huge plant. So it's such an important issue, chromium 6 emission. Now it is easier to detect, analyze and detect chromium species, which again 15-20 years ago it was very difficult to speciate between the different valence forms, but now you can do it. The analytical instruments have progressed so much. I cannot remember. So maybe you can find it out and then let us know on Tuesday. That's your homework. Okay. It will be important for your literature review. The whole trace element emission part in your literature review. Seriously, and it will be and if you can do that very well, you can publish it quite quickly. So the control of the chromium 6 emission or suppression of its emission, the literature is still divided, and the techniques therefore are still developing, even though you can measure them, but how to control them still unknown. So last time, about 4 or 5 years ago, when I really had interest, I saw that different universities, they were doing what is called the round robin tests. So what happens is different universities collaborate on a particular project, and everyone does the test at their condition, at a given condition, and the results are shared and compared. The whole idea is these are trace elements. These are very small amounts, nevertheless very, very important from the EPS point of view. So depending on how you measure, your values can be completely different from how someone else measures. So that's why the round robin tests are so important. We have participated in few round robin tests. That way the funding bodies forces us to collaborate amongst institutions. The idea is you all do it, and then the results are shared, and from that comes up a unified procedure that will then be adopted as a standard, international standard. That's how it is done. So it's no longer it is done by institution X or institution Y alone. It's institution X, Y, Z, W all combined together doing it. So that's the trace element emission. Let's go into the alkali and chlorides. So what are the alkalis and the chlorides? Hydrogen chloride is the predominant one. Very little bit, little is hydrogen fluoride, depending on if the chlorine is fluorinated coal. This country, I haven't come across any fluorinated coal, existence of fluorinated coal, not even in Australia. But sodium chloride is an issue because of the salty coal. So measured data for this species at pilot scale are rare, but I'm hoping that Saurabh will be doing it, these measurements here. Not difficult to do. When it is ready, let me know. Just keep a tapping point from your horizontal section between the two. Just keep a tapping point, keep it switch locked for the time being, do nothing else. Get the experiments, main experiment done, and then let's talk. I'll then tell you how to do it. I'll be pleased to tell you how to do it. Then the measured data for this species at pilot plant scale are rare. Gasifier. NaCl can be removed by reacting with aluminosilicate minerals, and that's what we demonstrated when we did our CFBC work that I showed in 5 or 6 slides on day 2 or day 3, I can't remember. How it works, the sodium chloride reacts with aluminosilicate, which is clay, and with steam, and then it makes sodium aluminosilicates, and then the hydrogen chloride gets out as vapor, and hydrogen chloride can be condensed out quite quickly. Or the other one is, of course, cool the gas down all along completely. That's it. HCl can be removed by sodium or calcium based minerals such as the nacolite or sodium carbonate or limestone or dolomite. So, the HCl. Then the calcium based minerals offer the possibility of removing both hydrogen sulfide and hydrogen chloride simultaneously at temperatures up to 700 degrees centigrade. So that's a good thing. So, so in all the doomsday scenario that we are presenting, not everything is bad really. In between there are some good flashes of good news that some of the species can be removed at the same time, hydrogen sulfide and ammonia, for example, together with iron-based oxides. Hydrogen sulfide and HCl at the same time, therefore, will be ammonia too as well. So there are a lot of things that we can actually study if we find out how much of these species are generating in the first place. So in your biomass case, for example, you'll be getting a lot of chlorides for sure. You'll be getting a lot of ammonia. You'll be unlikely to get much sulfide at all. But that ammonia and hydrogen chloride, you should be able to take it out quite easily. So is sodium chloride. So studies at pilot scale or higher are rare. Most studies are at laboratory or bench scale and far from commercial reality. I think if what you're going to have is a large bench scale, so that's good. Halide removal in hot gas cleaning should ideally be carried out ahead of particulate removal and desulfurization process. Why? To prevent reactions with the desulfurizing solvents and allow spent solvents and alkali salts to be collected in the ceramic filter. So that's common sense. So, well, even though I have mentioned here hot gas cleaning, but it is what I am really meaning in here, that you have seen all the temperature limits that I have shown in the previous tables. At best 700, but mostly around 500, 550, that range. So these are really warm gas. And there is no surer way of getting the alkali out completely than condensing, deep cleaning of it. So I still believe that based on what I find, I look for day to day, the developments in the large scale units anywhere in the world, there is still an opportunity and need and an opportunity to carry out these studies in a focused manner in large bench scale units, and that can only be possible in the universities. Private companies will be reluctant to do those on their own unless they are funded by governments or they have a vested interest to build a large plant which will give them immediate revenues. So there is the niche opportunity created for the researchers. So that's the gas cleanup for the time being, but that's not all the gas cleanup that I wanted to talk about. That's only the intro part of it. On Monday we'll continue on the theme. On Monday we'll also continue on the some of the pending questions. So you will give me that piece of paper and one pending from Saurav and you on the other day, which I haven't still finalized. So I will keep those in there. So Monday first half I want to do that. Second half, I think immediately after lunch we will have this session from the students. It was really interesting, and everyone presented with a lot of enthusiasm, and and the questions that were generated were, I'm sure all of them found to be useful. And of course, Dr. Davis' presentation was also very informative from the point of view of the practicality or the difficulties of what CCS entails. Okay. So any questions? Run the gasifier at slightly above atmosphere. Run the gasifier at slightly over atmosphere, or have in the coal-fired power plant. It's a good point. Good point. Coal-fired power plant. Current coal-fired power plant. Furnaces run at what pressure? Who can tell what's the pressure inside a coal-fired boiler, the one that is giving most possibly this electricity supply? Atmospheric. Correct. The fireball area, that's slightly under vacuum, but other than that, it's all atmospheric. But still, then, despite this being atmospheric, an enormous loop, superheaters, reheaters, economizers, air preheaters, back filters, long, tall chimney. How is it going there? What do you think? And then, what is at the end before the chimney? ID fan. Induced draft fan. So the point I'm making is, it's possible to engineer that problem out. Compared to this ones, that's a baby. Any other questions? So on that exciting note, let's finish this week, and we'll all come back with full renewed vigor on Monday morning. Okay? Enjoy your weekend, and enjoy it to the fullest, because you need to give yourself a bit of a prize. So in whichever way you want to do it, up to you, but give yourself a break. Don't think about work. There is more to life than work, just work. That's for people like me who have got nothing else to do. Your life is a lot ahead, so you should be enjoying.